All right. Shall we get started? Yeah, let's do it. Good morning, everybody. All right, thank you. Okay, today is going to be kind of a cool day where we get to combine everything together, right? Let's see if I'm getting my days right. First, we started with right triangle trig. We said, hey, you can take a right triangle, you can find all these measurements, you can set up these new ratios that describe how one side compares to the other, right? Those are pretty fine and dandy. It's like, that's great, but not everything is a right triangle. So we said, okay, you're right. How about any angle? We can describe any angle on the Cartesian plane as a rotation from the x-axis, right? And we described that stuff and converted with new unit called radians, right? And it's like, this is this weird new thing, okay? But trust me, you'll learn to like it. It is useful. And so what we're going to do today now is find the trig ratios of any angle on the Cartesian plane, right? Stick the two of them together, right? Pretty useful stuff. Before that, save to camera roll. No, I don't know what we're saving to camera roll, but okay. Before we do that, let's, wait. Before we do that, let's go over answers to your previous worksheet. Yes? So real quick, and then I gotta drag this over here. Okay, can you guys see that very well? It's a little washed out. We've got a lot of sunlight in here. There we go. Better. And, 810 lands exactly on the axis. So I would expect your arrows to be exactly on the axis. 185, not so much. Again, I told you how precise it needs to be. But you can also use a little bit of common sense and be like, oh wait, I know where 180 is. This is like barely a smidge over that, right? So we can, it's reasonable to have an estimate that looks closer to this than it does to this. That's a reasonable expectation. Be like, okay, you can distinguish that one right next to the axis. Right. But otherwise, yeah, you're either right in the middle of the quadrant, upper third of the quadrant, or the lower third of the quadrant. That's as close as I care to get, and that's as close as most angles we actually deal with get to be. Okay? And then here is the conversions. Okay, we can zoom in a little bit. There we go. I can't resize the window on here because then that changes how it appears on the video and throws the whole thing off. So if you need me to zoom in on something, let me know. Okay, the coterminal angles. Here is the next closest one. You could have something different. It does say sample answers for a reason. I didn't point this out from the previous worksheet we did, but any of those positive, just says, find one angle with a positive measure that is coterminal. So I could take 405 and I could add 360 again, right, and get 765, and that would also be correct. So if you have 765, you are also correct. It didn't specify the next closest. It said any of them, right? We can keep going around and around. It's like skateboarding tricks, right? Spin all the way around, you get 360. Do 2 spins, 720. You're still facing the same way. So keep spinning. Okay, that's the end of those. Questions there? All right, and they'd set this up funny, so I gotta like scroll over here. There's the other side. There. All the way over. There we go. Conversions. And coterminals. One more tick. There's the other word problem. Okay, any questions from here? No. That's okay. All right. Then let's go to the new thing. Let's talk 13.3. Okay. My window out of the way again. So, trigonometric functions of the general angles. And I'm just going to highlight a few things straight from the intervention worksheet here, because it's really simple. Really simple, guys. Here's what we're going to do. We've got our Cartesian plane here, right? You recognize x and y axis. And we have, let's not focus on the angle yet. Start with a point. Right? When they say general angle, for right now, they really mean for any point on the Cartesian plane. Okay? Because from that point, I can draw a ray from the origin through that point and treat that ray as an angle rotated from standard position up through that angle theta. Okay? And this, in pre-calc, you might talk about polar coordinates. It's another way to specify where something is. We can talk about where this point is in space based on its horizontal and vertical distances from 0, or we can talk about it as a distance r and an angle theta. You go this far out in that direction. That's polar coordinates. So really, this is the conversion between two coordinate systems. Okay? We're not going to worry about that quite yet. What I want you to see is that any dot can be connected to the origin. Okay? That's point number one. Any point in the Cartesian plane connects to the origin. Draw a line. Done. That line, or line segment, or ray, is the diagonal, is the hypotenuse of your right triangle. Any point in the Cartesian plane, you can draw a perpendicular to the x-axis, as they've done here. Okay? And I believe we talked about this already when I was just introducing you to standard position general angles. Apparently, I was already merging a bit from section 3 here. Right? So from any point, connect to the origin. There's your hypotenuse. Connect to the x-axis. Draw your altitude down to create a right triangle. And now I've created, out of any point in space, in the plane, technically, okay, in the plane, I've created a right triangle. From this right triangle, we can do trig ratios, right? I know my hypotenuse. I know x, we can find y. Right? Or I know y, we can find x and r, or right, any combination of two pieces of information. If we only have sides, we know Pythagorean theorem applies, right? Remember that guy? So you can find the third side. You can easily get up to all three sides. From any two, we can get the third. And now we can combine any ratio, and we can get the angle, right? So here then are the trig functions in terms of these guys here. So instead of opposite, adjacent, hypotenuse, we are now going to refer to the sides of our right triangle as x, y, and r. Okay? This is the new standard. Opposite, adjacent, hypotenuse is a good descriptive format. Okay? But we need a more generally applicable algebra format. So I want you to work on this. Start bringing this locked into your brain. How do you find the height? Height. How tall something is. Okay? Exactly as it looks in the diagram. How much up? That's y, right? Y we usually use for height. Pretend this is the horizontal. How tall up? Y. How do you find y? Which trig ratio is associated with y and only y? No x. Don't involve x. I don't care about the length. I just wanted the height. Sine. Okay? Sine gives you height of y. Y. What about that r? Right? I hear the question in your mind, Mr. Apple. What about the r? You said no x. Why can't? What about r? Doesn't that interfere with things too? The secret is, most of the time, we are going to set r ourselves. In the general case, as they're introducing here in the text, yes, r could end up as anything because they'll give you just some random point. Okay? And we'll go through the example in a moment. But most of the time, we're dealing with the unit circle. We are pretending within a circle around the origin, whose radius is set to be 1, we can find the height. Because imagine, if r is 1, look at this. Sine is y divided by 1. Cosine is x divided by 1, right? That simplifies things immensely, doesn't it? And then, sine always gives you the height. Cosine always gives you the horizontal distance. All by itself, because we made the denominator 1. See how useful that can be? I think I would just said radius to 1. Easy peasy, right? So that is what we're aiming for. That's going to be super convenient. Now, these examples here, again, the most general from any point along the plane. Take the point -5, 5 root 2. Oh gosh, they had to throw in a rational in there. How obnoxious. Right? Don't worry, we'll take care of it. First up, Pythagorean theorem, right? This point up here, they are, by definition, the x and the y coordinates of the point. So they tell us the x and the y lengths. We already have the two legs of a right triangle. Pythagorean theorem, straight up, find the hypotenuse. R is square root of -5 squared plus 5 root 2 squared, square root of 75, or 5 root 3. Okay? There's a hypotenuse length. Done. We're halfway there. We've got 3 out of 6 things to solve for. The triangle. Find all 3 sides, find all 3 angles. The triangle is solved. So now we can use those 3 sides. We can write any ratio that we want, just like the first section. Okay? Here are the 3 sides of a right triangle. Find the 6 trigonometric ratios. You know how to do this. And you can pick any of them you like and use the inverse trig function. Let's pick cosine. Okay? If I want theta, so theta, to solve for theta, is going to be cosine inverse of x over r, or in this case, of negative root 3 over 3. Okay? Type that in the calculator. Boom. There's your angle. This is the part where you do have to be careful of your mode on your calculator. Maybe some of you already encountered that. You check that. Calculator mode. Make sure if you want the degree answer, you got to be in degree mode. If you want the radian answer, you have to be in radian mode. Right? This is the chapter where the calculator modes will throw you off. Double check that. So now we can solve anything for any triangle formed from any point anywhere. Agreed? Any questions about this process? Okay, so there's some practice there. Back side of the worksheet. The other thing they add to this section, we already covered. I don't know why they didn't just bring this up with the angles in standard position in the first place? I already did. I already told you about this. Reference angle, right? Any angle from anywhere, the thing you actually want to do the trig part, to form the triangle, is to draw a line to the x-axis and now find the angle between your ray and the x-axis. Even if it went all the way up and around, no, from you guys you're reversed, right? Start standard position, up over here. I don't want this gigantic angle. That's more than 90. We can't have an angle more than 90 inside of our right triangle. So we want this angle, right? Find your reference angle. Covered. And then they talk about the signs of the trig functions in each quadrant. You can memorize this chart. This chart is, well, it works, but it's not very intuitive, okay? There's a really dumb mnemonic. I think I've already said it already. Right? Start quadrant 1, 2, 3, 4. ASTC. You can create any acronym you like. I'm still stuck with all students take calculus because that's what was drilled into my head in high school. You can have all students taste chocolate. I don't know, right? Alabama squiggles tangentially car. No, that one doesn't work, right? Make up something, right? ASTC. Okay? There's your ASTC. All of them are positive. Right, this tells you which are positive. All are positive over here. Sine is positive here. Tangent is positive here. And cosine is positive there. Anything else or anywhere else is negative. That's all you need to remember. And really, you don't even need to remember that. Because if you can remember these, you can work out what sign it has to be, right? R has no sign, right? But your x and y coordinates will have signs on them, right? Over here, x is going to be a negative number, isn't it? So anytime there's an x involved, look, cosine, that turns negative, sine stays positive. Tangent, that has an x is negative, y is positive, tangent turns negative, doesn't it? Right? That's all you really need. The other half is extra. Okay. Any questions on that bit? No? All right. Now, I am now going to build for you the most useful thing you can possibly have in this whole trig chapter, the unit circle. Right here, and I'm going to use a blank one. So if you do not have one of these in your notes already, please follow along with me. Draw such a thing in your notes. We're going to start with quadrant 1. Right. And so just whip up a quick, nice big set of axes. Okay, take up a quarter of the page. Give yourself lots of room. We're going to shove a bunch of numbers into this thing. And a little arc, like that. So it looks kind of like a quarter of a circle. Right? It doesn't have to be super artistic. If you want to draw a nice, great big circle, take up a whole page, go for it. I'm going to fill this thing out from memory. And I'm going to explain to you how I actually remember it all. Because there's a lot of stuff that goes in this circle. Right? I do not have the whole thing memorized from scratch. I remember a few key pieces and a few key relationships that let me build up the rest of the circle. Okay? So I'm going to try to color code mine just to keep it as clear as possible, because like I said, a lot of stuff to go on here. Now, for every quadrant in the circle, we have 5 critical points, right? We have the 2 that land on the axes, and we have 3 in the middle. 1 is dead center. Right? We've been talking about that before, and then 1 below and 1 above that. Where are those points? I'm going to start with the angles. On the positive x-axis in quadrant 1, this is 0 degrees. And it's also 0 radians. That looks like a big fat O. Let me see if I can make it a C in here. 0 rad / 0 degrees. Okay. I'm going to put my angle measures on the inside of my circle. Okay. And then up here at the tippy top, at the y-axis is, we know that one is 90 degrees, or in radians. Shoot, I don't remember the thing in radians. All right, zoom back out a moment. I know the whole circle all the way around is 2 pi radians, so half the circle is pi radians. I'm going to note that down since I'll need it later anyways. And that means this is half of that. Oh yeah, that's pi over 2. Okay? When you're in the middle of working with this stuff, that'll come to you. You'll be able to remember that off the bat. That's one's simple enough. You can recall that instantly. I'm going cold from this, right? I haven't prepped this. This is how I generate this thing from scratch every time. Pi over 2 radians up there. And then I'm going to go next easiest is halfway down the middle, bisecting things. Super simple stuff, right? So that means this middle dot is 45 degrees. Or, well, that was pi over 2, so half of pi over 2 is pi over 4 radians. And I'm not going to write radians every time. It's going to take up a lot of space. Okay. Next, we got those other 2 dots. Those other 2 dots come out of my special triangles from geometry. We had the 45, 45, 90. Well, that's already covered. I got 45. The other special triangle is the 30, 60, 90 triangle. So that means those 2 numbers get 30 and 60 respectively. This one is clearly the smaller one, so it must be 30 degrees. This must be 60 degrees. I hate my numbers overlapping here. Yep. And can you see now, from this quadrant, I could fill in the rest of the degrees in the other quadrants, yes? We could just continue adding 30 degrees, add your 30 degrees every time, right? So plus 30, plus 30. Notice I skipped that one. The half guy is still the 45, right? So you go plus 30, plus 30, plus 30. We could work our way all the way around. For those of you that have a full angle, just present that. Just one more quadrant. 90 plus 30 makes 120. 120 plus 30 makes 150. 150 plus 30 makes 180. Oh, yeah, that was half my circle. Check. All right, we could keep going. For the sake of brevity, I'm just going to do the first quadrant. Well, I want you to see how that quadrant extrapolates to the rest of the circle. You don't need to memorize the whole circle. You only need to remember one quadrant, and then how to get the rest of them, if you need them. In fact, you don't even need the whole quadrant, right? Because this 60-degree angle is intimately related to this 30-degree angle. Every number we put here will appear up there as well. That's pretty handy. In fact, the next thing I need to do, I need my radian measures for the 30 and the 60. Anybody know what 30 degrees is in radians? Top of your head? Neither do I. I don't remember. But I do remember what numbers are involved. And it's the exact same numbers we have here, a 6 and a 3. Everything in radians is pi over something, right? We've picked up on that so far. Kind of Get a feel for that? A pi over 6 and a pi over 3, right? That sounds pretty reasonable. Those should fit. That's how much I remember. I've remembered, hard-coded, like it's got to be those same numbers used again in the denominators, 6 and 3. Which one goes where? Which one is the smaller one? A sixth of a pi or a third of a pi? I know which I would rather eat. So the smaller one's the other guy. The sixth of a pi, right? So pi over 6 must go here. And pi over 3 goes up here. These are far and away the most common angles used for literally everything. Okay. Most of the questions from your book. Most of the questions, I dare to say almost exclusively, certainly on the no calculator portion of the SAT, all the angles come from these, or the other quadrants as well, right? The unit circle, this is why we call it the unit circle. It's a big deal. These are the most commonly used. And in all applications, right? Real life construction stuff. Look at all the triangles we have in this building right now, right? We've got a bit of an exposed roof structure. We can look at this lattice up there. Those are all made out of equilateral triangles. The angles in an equilateral triangle. Guys? Thank you. 60 degrees. Let's not like totally forget geometry here. Right? How about that corner right there? If I diagonal across the corner, that's a 45, 45, 90, right? Special triangles are everywhere. So we use those special triangle angles on our unit circle. It makes the trig super easy, because now we get the same results. The same numbers show up all the time. Okay. Now here's the next bit. We can find, remember I said, beginning of the section, we can find the sine and cosine and the other relationships from any point in the Cartesian plane. We can also go backwards. We can go the other way. Knowing the sine and cosine of an angle, we can determine the coordinates of that point in the Cartesian plane. Does that make sense? We can, right? We should be able to do that. I am now going to write the coordinates of all these dots here. Again, not entirely from memory. I've only memorized a little bit of it. Let's start with the easiest ones, right here. This is called the unit circle, right? There it is, unit circle. Which means my radius is how much? 1, the unit, right? Whatever units of measure you use, call it inches, centimeters, whatever your distance units are, we have one of those, the unit, okay? 1 unit. So if our radius is 1, and you just head out 1 unit on the x-axis, your coordinates will be 1, 0, right? And straight up the y-axis is 0, 1. Those are the easiest. In fact, let's just fill the rest, right? This has to be -1, 0. And this guy down here would be, outside. Coordinates on the outside. 0, -1. Right there. Okay. They're all on screen. So if you want to see the full picture, there it is. This serves as your reference of what sign goes where, right? Oh yeah, the x's are positive, y's are positive, right? Oh, x is negative, right? Y is negative, right? So these 4 points, you fill it in your circle, serve you as a reminder of what signs need to go where. Zooming back in on just the one quadrant here, because this is the most important bit. This is all we need. I told you to memorize 1 trig ratio. What was that? Sine of what angle? 30 degrees, very good, is what? Oh no, they haven't memorized it. Sine of 30 degrees is a half. 1/2. Sine of 30 degrees is 1/2. Memorize that one. When I told you the unit circle is all of the trig on the no calculator SAT portion, most of the trig on the calculator portion. Sometimes they'll get you and be like, oh, you can use your calculator, so find sine of 274 degrees, right? So they can do that to you there. The first quadrant is most of it. So not only is the unit circle itself the most common of the unit circle, first quadrant. The most common of the most common of the most commonly used angle, 30 degrees. And every time when you list out all the trig functions, what do you start with? Sine is the first one on the list. Every time they do it. Why not pick up on that? If you had to memorize one of them, far and away, the most common ever, sine of 30 degrees is a half. And we said the sine gives you which coordinate? You've got two choices, 50-50 shot. Make a guess. What do you think? Raise your hand if you think it's X. Nobody thinks X. Raise your hand if you think it's Y. Ooh, we've got some votes for Y. It is Y. Sine gives you Y. So that means my Y coordinate here is 1/2. Right. Relationally, the 60 degree, right, is the complement, literally complementary within that 30, 60, 90 triangle. But it's backwards. So the X coordinate on my 60 degree is a half. And let me just set up the rest from there. Yes, this means I could remember that cosine of 60 degrees is a half. But I don't remember that fact like that. I remember sine of 30 is a half. And I work out that, well, that must mean that cosine of 60, if I like invert and invert again, complement of a complement is back to the same number. Okay? With me so far? There's only two other numbers we need. That's it. There's two other values that fill the rest of these blanks. And they are the irrational sides of the special triangles. Right? We had two irrational numbers out of our special triangles, square root of 2 and square root of 3. Right? And everything is over 1/2. So if you remember one little fact, wait, everything is a something half. It's all something over 2. I remember that part. Question is, what over 2? What goes where? Square roots of 2s and square roots of 3s, because those were the irrational numbers from our special triangles. Well, this is where my next fact that I've actually remembered comes in. This guy right here, the pi over 4, or the 45 degree, right smack in the middle, the isosceles special right triangle, right? He's got symmetry going for him, right? Right smack in the middle of the quadrant? Seems reasonable? So that means not only are the x and y values exactly equal to each other, we could see that, it's on the diagonal there, we know the x is equal to y there. But there's also symmetry up and down. The numerator and the denominator show a little bit of symmetry. So which irrational number do you think should go there? Samantha, what do you think? Which one? Square root of 2 or square root of 3? Square root of 2, right? Because then I got 2 up top and 2 on bottom. Mr. Apple said there's a little symmetry there. That's what I'm talking about. We get the same number there. It's like, oh, they made it easy for us. Square root 2 over 2 goes there on the 45 guy. The only other number left, the one I haven't used yet, is square root of 3. Oh. Look at that. From knowing my special right triangles, knowing just a couple rules, I can work out and recall that cosine of 30 degrees is square root 3 over 2. I haven't actually memorized that statement as is. I remember sine of 30 is a half. And so cosine must give me the other one. Right? That's what I remember. That's how I work it out in my head. If that helps you, great. If you want to just plug and chug, and just, I'm just going hardcore memorization, go for it. You can do more than that. But I'm sharing with you my bare minimum, okay? The fewest memory bits required. And the rest of this flows from that. All of these numbers get duplicated, right? The only thing that changes is the sign. So I'm going to take all of these. I'm going to rewrite this one goes here. This one goes here. This one goes here, right? They just zip straight across. Agreed? Because they're at the same height, aren't they? The same y value. Remember, this is still a Cartesian plane. This goes zip right across. Square root 3 over 2 and 1/2. X, y, x, y. Except what changed? X is now negative, right? So I take all these, copy them as is. I'm going to cheat here. I've got a copy tool, right? Copy, paste. There's the coordinates for that guy, except make the x negative, right? Look at that. We've now got half a circle. Except make the x negative. Copy that, paste, except make the x negative. I've got half a circle. Look at that. So much good stuff. And from half a circle, can't we just duplicate downwards and make a whole circle? Absolutely. Except what? If I move this down here, right, and just take this thing straight down, the x didn't change. The y height flipped over, and so now the y is negative, right? So the whole bottom half of the unit circle is exactly the same as the whole top half of the unit circle, except all the y values get negative. Right? That's the only thing that changes. Just watch your signs, and you can fill the whole thing out. Other things you might want to remember, you should be able to recognize this guy right away. Right? Half the circle is pi radians, 180 degrees. We didn't do 3/4 of the circle. Let's fill that one in at least. This is 270 degrees, or 3 pi over 2 radians. And of course, back all the way around, 360 degrees, or 2 pi radians. Full circle. Gets you back to the same point. Those ones are worth memorizing. The others, again, you can fill in. Just keep counting, right? 150, 180, 210. Skip the 45 guy. The 45 guy counts independently. So either you are moving every 45 degrees, hitting the axes and the diagonals, or you're counting every 30 degrees, right? And you hit every third a quadrant and the axes. And you just count around, add them up. Okay? Any questions there about the unit circle itself? What are you going to do with this? This is a handy-dandy reference chart, okay? The more you have filled in on your unit circle, the better tool it will be while you're doing your homework, and you can just look up and be like, ooh, hey, it says cosine of 150 degrees. You can look at your unit circle and be like, 150 degrees, there it is. Cosine gives me the x value, what is that? There it is, right? Save yourself some brain power. You thought of it ahead of time when you built the thing. Now you use it. It's a tool. Now, the question everybody wants to know, can I use such a tool on a test? Now, this year, I've been letting you use all your notes on the test so far. So absolutely, yes. You have this whole thing created. Fill the rest of it in, please do. And then that'll make your testing life much easier. In the future, you might not be allowed to use all of your notes on a test. You might not be allowed to even use a filled-in unit circle on the test. Which is why I gave you those mnemonics, how you can remember just a little bit and create the whole thing from scratch. Whenever I took a trig test or a test that involved any trigonometry, one of the first things I would do, I would flip the test over to the blank page on the back, and I would create from scratch, out of memory, my unit circle, because I knew I would need it. Like, okay, I know this teacher. They're not that nice to actually have all the questions be about sine of 30 degrees. I'm sure there's going to be something in like the third quadrant somewhere, so I'm going to need those numbers eventually, right? So I built it up. And then it was very easy to flip and reference and be like, oh yeah, it's that, done, done, done. Just makes the whole thing so easy. Right? Your worksheet for today is that 13.3 section worksheet. Okay? The unit circle here will help you do that faster and easier. Next week, okay, on our second day of the section, your work there will be explicitly the unit circle. Okay? So we'll have more practice with it. Clear? Questions? No? We have only a couple minutes left. This is a bit of a long one, but I'm hoping it was extra useful for you. So take a couple minutes, look at that worksheet, skim through it, see, hey, is there anything that stands out to you? It's like, ooh, wait, I don't know what to do with that. Okay. Get that question answered now. Otherwise, we'll